For as long as human beings have looked up at the night sky, we have asked the same question. Is there another world out there like ours? Not a gas giant swirling with storms, not a scorched rock orbiting too close to a furnace, not a frozen wasteland drifting at the edge of a solar system's reach. Something like Earth, blue, warm, wet, with an atmosphere that breathes, with liquid water on its surface, with a sun close enough to give warmth but not so close it strips everything away. A world where something might live. For most of human history, this was philosophy, poetry, religion, a question that science had no tools to even approach, let alone answer. Then we built the tools. And in the data that came back, in the light curves of distant stars and the spectral signatures of alien atmospheres, we found something that stopped scientists in their tracks. A planet, small enough to be rocky, warm enough for liquid water, orbiting in the habitable zone of its star, with a size, a mass, and a set of characteristics closer to Earth than anything ever found before. Its existence has been confirmed. Its coordinates are known. Its star is close enough by galactic standards that future instruments might one day tell us whether its atmosphere carries the chemistry of life. And finding it, understanding what it is, what it tells us, and what it means for the oldest question our species has ever asked, is one of the most profound scientific achievements of our era. This is the story of the most Earth-like planet ever found. And it begins not with the planet itself. It begins with everything we searched through before we found it. For most of the 20th century, we did not know whether other stars had planets at all. We suspected, logically it seemed almost impossible that our sun alone among hundreds of billions of stars in the Milky Way should have the privilege of planetary companions. But suspicion and evidence are very different things. The first confirmed detection of a planet orbiting another star, an exoplanet, came in 1992, and it arrived in the least romantic setting imaginable. The planet was not orbiting a sun-like star, it was orbiting a pulsar, a dead, collapsed, rapidly spinning neutron star that sweeps beams of radiation across the cosmos like a cosmic lighthouse. An environment of extraordinary radiation and gravitational extremity, about as far from a habitable world as anything in the universe. Not a promising start. Then, in 1995, came the first confirmed exoplanet around the Sun-like star, 51 Pegasi b, a gas giant, hot, enormous, orbiting its star in just 4 days, a so-called hot Jupiter, far too hostile and far too massive to harbor life as we understand it. Still not Earth. But the tools were working, the methods were validated, the hunt was on. In 2009, NASA launched the Kepler Space Telescope. Its mission was simple in concept, extraordinary in ambition. Stare at a patch of sky containing approximately 150,000 stars for 4 years. Watch for transits, the tiny, predictable dips in starlight caused by planets passing in front of their host stars. Measure the size of those planets, calculate their orbital distances, find the ones in the habitable zone, find the ones that might be like Earth. What Kepler returned over its 9-year operational life was staggering. Over 2,600 confirmed exoplanets, thousands more candidates awaiting confirmation. Planets of every conceivable size, temperature, composition, and orbital configuration. Super-Earths, mini-Neptunes, lava worlds, ice worlds, hot Jupiters, and scattered among them, rare, precious, deeply exciting, a small number of roughly Earth-sized planets in the habitable zones of their stars. Each one of these brought us closer to the question. But Kepler had a limitation. The stars it watched were mostly distant, hundreds or thousands of light years away, close enough to detect planets, too far away for the next generation of telescopes to study those planets in the detail we truly needed. We needed an Earth-like planet around the nearby star. And in 2017, NASA launched TESS, the Transiting Exoplanet Survey Satellite. Where Kepler had stared at distant stars, TESS surveyed the sky's brightest, nearest stars, hundreds of thousands of them, creating a catalog of exoplanet candidates orbiting stars close enough for detailed atmospheric follow-up. The stage was set, the instruments were ready, and the data that came back from one particular star, small, quiet, relatively nearby, contained a signal that became the most exciting exoplanet discovery of the decade. The star is called TOI 700. It is an M-dwarf, a red dwarf star. Small, cool, and dim by stellar standards, only about 40% the size of our Sun, burning at a fraction of the temperature, emitting mostly infrared and red light rather than the white-yellow light of a Sun-like star. Red dwarf stars are the most common type of star in the galaxy. Roughly 70 to 75% of all stars in the Milky Way are red dwarfs. They are also extraordinarily long-lived. Where our Sun will burn for about 10 billion years total, a red dwarf can burn for tens or even hundreds of billions of years, far longer than the current age of the universe. TOI 700 sits about 100 light-years from Earth, in the constellation Dorado, close enough by astronomical standards to be considered a neighbor. And orbiting TOI 700 in the habitable zone, the region around the star where liquid water could theoretically exist on a planetary surface, is a planet designated TOI 700e. TOI 700e is remarkable. Its radius is approximately 0.95 times that of Earth's, 95% of Earth's radius. For all practical purposes, Earth-sized. Its mass is estimated at around 0.85 to 1.1 Earth masses. Again, for all practical purposes, Earth mass. It orbits its star in approximately 28 Earth days, which sounds fast by Earth standards. Our year is 365 days, but because TOI 700 is a much cooler, dimmer star than our Sun, the habitable zone is much closer in. A 28-day orbit places TOI 700e comfortably within the range where liquid water could theoretically exist on its surface. Its equilibrium temperature, the temperature it would reach if it absorbed and re-emitted stellar energy with no atmospheric effect, is estimated to be close to Earth's, possibly slightly cooler, possibly in the range where water remains liquid under the right atmospheric conditions. Size: Earth. Mass: Earth. Temperature zone: Earth. It is, by every metric we can currently measure, the most Earth-like planet ever confirmed. But there is a complication, an important one that honest science cannot sweep under the carpet for the sake of a clean, triumphant narrative. TOI 700e is almost certainly tidally locked to its star. Like our moon is locked to Earth, always showing the same face, a planet orbiting a red dwarf this closely is likely locked in the same way. One hemisphere in permanent day, one in permanent night. On Earth, this would be catastrophic. Our weather, our ocean circulation, our climate systems all depend on the rotation that creates day and night. A tidally locked Earth would have a scorched desert day side and a frozen, perpetually dark night side. But here is what climate models, increasingly sophisticated, simulations of what a tidally locked Earth-sized planet might be like, have begun to suggest. It might not be as hostile as it sounds. If TOI 700e has an atmosphere, even a modest one, atmospheric circulation could transfer heat from the day side to the night side. Winds could moderate the temperature extremes. Clouds on the day side could reflect stellar radiation, cooling the day hemisphere. The terminator, the boundary line between permanent day and permanent night, might be a temperate zone, a band of eternal sunrise and sunset, where temperatures are moderate and liquid water is plausible. Not Earth, but perhaps not uninhabitable either. the question of what TOI 700E's atmosphere actually contains, whether it has one at all, and if so, what gases are present, is the question that the next chapter of this story must answer. TOI 700 is close enough, and TOI 700E is small enough, and the geometry is favorable enough that James Webb can attempt to characterize its atmosphere. Not easily, not quickly, not in a single observation. Atmospheric characterization of a small, rocky planet around a red dwarf is one of the hardest things Webb can attempt. It requires dozens of transits observed across months or years, each transit adding a tiny amount of information to an accumulating picture, each observation building on the last until eventually a spectral signature emerges, or does not emerge. If TOI 700E has no atmosphere, if it is a bare rock stripped of its gases by the radiation and stellar flares that red dwarfs produce in their early, more volatile years, Webb will detect a flat, featureless spectrum. No molecular signatures, no atmospheric chemistry, just reflected starlight. Disappointing, but informative. Another data point in our understanding of which planets can hold on to their atmospheres and which cannot. But if TOI 700E has an atmosphere, if something about its size, its mass, its magnetic field, or its distance from its star has allowed it to retain a gaseous envelope, then Webb might detect something. Water vapor would be the holy grail, the molecule most directly associated with conditions for life as we know it. Its presence in an atmosphere at the right temperature and pressure would represent the most significant exoplanet discovery in the history of astronomy. Carbon dioxide would tell us about atmospheric thickness and chemistry. Methane, in combination with carbon dioxide, would raise the extraordinary possibility of biological activity, because in the presence of both molecules, the methane should quickly be destroyed by chemical reactions, and its continued presence would require constant replenishment. On Earth, that replenishment comes largely from living organisms. Oxygen, if detected, would be the most dramatic signal of all. Molecular oxygen is highly reactive. It bonds readily with other elements and disappears from atmospheres on geological timescales, unless it is constantly being produced. On Earth, the oxygen in our atmosphere is almost entirely of biological origin, produced by photosynthetic organisms over billions of years. Oxygen in the atmosphere of TOI 700E would not be proof of life, but it would be the most compelling evidence ever gathered that life might exist beyond Earth. Webb has already begun observations. The data is being collected and analyzed. The results, when they are published, will be among the most closely watched scientific announcements in human history. We are waiting. And the waiting itself is an extraordinary thing. For the first time in the history of our species, we are not waiting to know whether other Earth-like planets exist. We have found one. We know where it is. We know its size and its mass and its orbital distance and its temperature range. We are waiting to find out whether it breathes. Let us sit with what this means. Not the science, not the measurements and the spectral analysis and the transit photometry. Those are the tools, the means. Let us sit with what it would mean, truly mean, if the data coming back from James Webb showed water vapor in the atmosphere of TOI 700E. If it showed the chemical fingerprints of an active, cycling, living world. For all of human history, we have been alone. Not alone in the dramatic, frightening sense of the word, not alone in a universe that seems indifferent to us. We have always had each other. We have always had this planet with its extraordinary richness of life and variety and beauty, but alone in the cosmic sense. As far as we have ever been able to confirm, in the entirety of the observable universe, in the 2 trillion galaxies, each containing hundreds of billions of stars across 93 billion light-years of space, we have found exactly one world with life on it. This one. One sample, one data point. No way to know if we are typical or extraordinary. No way to know if life is a natural, almost inevitable consequence of the right conditions, or a vanishingly rare accident that happened once and may never happen again. The detection of biosignatures on TOY 700E would end that uncertainty. Not completely, not with absolute certainty. Science never delivers absolute certainty. The evidence would need to be scrutinized, challenged, replicated, debated, refined. But it would change the question. From "are we alone," which has only two possible answers, yes or no, to something richer, something that opens into a universe of new questions. How common is life? How similar or how different? How long has it been there? Are we looking at something in its earliest stages, or something far more ancient than our own biosphere? And underneath all of those questions, one that is harder to articulate but more fundamental than any of them. What does it mean for us? What does it mean for what we are, for why we are here? For the story we tell ourselves about our place in the cosmos, if the universe turns out to be alive in more places than one? We have been the only story we knew, the only example of a world that woke up and looked at itself and asked questions, the only planet we could point to and say, here is where it happened. Here is where the universe, for at least one brief and extraordinary moment, became conscious of itself. Another living world would not diminish that. It would multiply it. It would mean the universe has a habit of this, a tendency, an inclination toward complexity and chemistry and the emergence of things that grow and breathe and eventually, perhaps, look up at the stars and wonder. TOY 700E is 100 light-years away. We will never visit it, not in any foreseeable future, not with any technology currently imaginable. 100 light-years is a journey of millions of years at the speeds of our fastest spacecraft. But we can see it, we can study it. We can read its atmosphere in the light that passes through it as it crosses in front of its star. We can ask the question. And the answer, whatever it turns out to be, will be the most important thing our species has ever learned. Because if the answer is yes, if the data shows water and chemistry and the fingerprints of a living world, then we will know something we have never known before. That life does not belong to Earth. It belongs to the universe. And the universe, it turns out, is generous with it. We have been looking for another Earth for a long time. We found one. Now we wait to find out if it is truly like home.